Good day, everyone. Welcome to lecture 27 of this lecture series on computer organization and architecture. In this particular lecture, we will be discussing about the control hazards and how to handle control hazards. So in our previous lecture, we were discussing about raw hazards, okay, or we can say about the data hazards. And we discussed how to handle such hazards. And while handling those hazards, we provided two solutions. One was a software solution and another was a hardware solution. Okay. Likewise, there is another kind of hazard that is there in pipelining, and that is a control hazard. So we have to discuss a control hazard and we have to discuss a mechanism to handle such hazard. Okay, so let's first briefly discuss what a control hazard is. So control hazard is when there is a branch instruction. Branch instruction. So first of all, a branch instruction, they are of two types. Branch instructions are of two types. One is an unconditional branch and another is a conditional branch. So what is an unconditional branch? Unconditional branch means a branch that is not checking any condition before making a jump or before making a branch. For example, call. Call is a branch because it is changing the program execution from one location to another location. So call is a branch and it is an unconditional branch, means whenever we have a function call, that particular branch will always be taken. Okay, so unconditional branch is always taken. Always taken. Okay, then comes a conditional branch. So conditional branch is a branch instruction that before taking a branch, it checks a condition. Okay, if the condition is true, the branch is taken. Otherwise, branch is not taken. So based on a condition, it can be a taken branch or it can be a not taken branch. Okay, so these are the two scenarios. So now let's see some example here. A simple example. For example, let's say we have instruction 1. Let's say this is our program. Instruction 2. Okay, instruction 3. Let's say our instruction 3 is a branch instruction. Fine. And the branch target is here. Let's say the branch target is, it's address 1, it is address 2, it is address 3. Let's say the address here is 10. Okay, so at address 4 we will have instruction I4. At address 5 we will have instruction I5, and so on. Let's say at address 10 we have instruction I10. Okay, let's say we are executing this program. Fine. So when we are executing this program, so first we will execute I1, then we will execute I2. Okay, then we are going to execute I3, but we know I3 is a branch instruction, so we will check this branch instruction. Okay, and for example, if this is an unconditional branch means a branch which is always taken. So that means this particular branch will be always taken. So after this instruction, what instruction will be executed? This I10 will be executed, and following the other instructions, if this is an unconditional branch. However, if this is a conditional branch, okay, so this branch checks a condition. If the condition is true, then it will be a taken branch. Taken branch means the next instruction that is to be executed is determined by this address, which is called a branch target. Branch target. So next instruction that is to be executed will be I10. However, if the branch is not taken, okay, or we can say the condition is not true and as a result branch is not taken. So what will be the next instruction? Then the next instruction will be I4. Okay, so if a branch is taken, we have to change the program execution, or we have to move from the sequential execution. Sequential execution means one after another. So if a branch is taken, we have to change from a sequential execution to a non-sequential execution. Okay, that means we are not executing instructions one after another, but we are executing a one instruction, and after that instruction we are executing some other instruction which is lying some X addresses ahead. Okay, and branches are of two types. So as I said, a branch can be an unconditional branch or conditional branch. Okay, so in conditional branch we have two types of branches. One branch is that branch which is making a jump to some location which is ahead of this instruction. So let's say here 10 is ahead of address 3. So such kind of branch is called a forward jumping branch. What does that mean? That means this branch, its branch target is ahead of its own address. However, if it is branch target, if the branch target of a branch is some address preceding its own address, then in that particular scenario, the branch is called a backward jumping branch. Okay, so this was about a branch. Now let's see what is the problem when we execute a branch instruction in a pipeline. Let's say we have this kind of program. Okay, so let's make a pipeline diagram and see how this program will be executed. So I'm making a pipeline diagram here. Let's make a pipeline diagram. Instruction fetch, operand fetch, execute. Okay, execute, memory access, write back. And these are our cycles. This is our cycle 1, cycle 2, cycle 3, cycle 4, cycle 5, 6, 7, 8, 9, 10, 11. Okay, so now let's see how this program is executed. So what will be the first instruction? I1. So what will happen in cycle 1? I1 will be fetched. Now in cycle 2, I1 will move to operand fetch and I2 will be fetched. In cycle 3, I1 will move to execute, I2 will move to operand fetch, and I3 will be fetched. Okay, now I3, we know I3 is a branch instruction. Okay, so in the fourth cycle, I1 will come to memory access, I2 will come to execute, I3 will come to operand fetch. Okay, so we know this I3 is a branch instruction. So what will be the next instruction that is to be executed? If it is a conditional, unconditional branch, then the next instruction will be I10. However, if it is a conditional branch, okay, so that means it has to check a condition. And we know a branch checks a condition in an execute stage. So only in execute stage, we will be knowing whether this branch is taken or not taken. However, at cycle 4, I3 is in which stage? Operand fetch. Let's say we are not handling this scenario. Okay, so we are allowing this instruction to go on. So what will be the next instruction that is to be fetched? Instruction I4 will be fetched. Now in the fifth cycle, I1 will come here, I2 will come to memory access, I3 will come to execute, I4 will come to here, I5 will come to fetch. Okay, now here I3 was our branch. Okay, now when I3 is in execute stage, so it is in execute stage, so at this particular point we will be knowing whether the branch is taken or not taken. Okay, so at this stage, at execute stage, let's say branch is not taken, not taken. Okay, if the branch is not taken, then what should have been the next instruction? Next instruction should have been I4, and we can see the next instruction is I4, is actually I4. But this is a scenario when the branch is not taken. Now let us see if the branch is taken. Okay, which branch is taken? I3 branch is taken. Then what should be the next instruction? I10 should be the next instruction. So if the branch is taken, should we execute these instructions? No, we should not execute these instructions. So in that particular case, we can say that here, if you said there are two paths, one path is this path, another path is this path. Okay, however, if the branch is taken, this path is the correct path and this path is the wrong path. So these instructions are in wrong path, so we don't have to execute these instructions. Okay, but if we are not handling this, you can see this I4 and I5 is already there in the pipeline, so they are getting executed. Okay, so when we are in execute stage, we are well sure that the branch is taken, so we have to neglect these instructions, or we have to remove these instructions. Or we can say that if we are not handling such type of cases, such type of hazard, then I1 will be executed, I2 will also be executed, I3 will also be executed, I4 will be executed, I5 will be executed, if we didn't handle this scenario. Okay, what scenario? This particular scenario. So you can see, for example, if in the sixth cycle, this would have completed, I2 will come here, I3 will come here, I4 will come here, I5 will come here. So what will be the next instruction that will be fetched if the branch is taken? The next instruction will be I10. Okay, I10. We can see that these two instructions, I4 and I5, these should not have been executed. However, if we are allowing this pipeline to go as it is, then it is executing these two instructions as well. So this will be an incorrect behavior. And this incorrect behavior is because of taken branches. And if we didn't handle this behavior, then there will be an incorrect result. And such type of hazard because of branches is called a control hazard. And we need a mechanism to handle this scenario. Okay, so we need a mechanism so that we don't have any instructions that are in the wrong path in the pipeline. Okay, so what I am saying that we have to handle. So let me first say that if we didn't handle control hazards, then what will be the issue? There will be instructions in pipeline which are in wrong path. Or we can say there are instructions which should not have been executed will get executed. So we have to handle such hazards, such control hazards. So let's see how we can handle a control hazard. What are the various solutions? So first solution is stall the pipeline. Stall the pipeline. So let me show you what this means is stall the pipeline. So let's come to the same scenario. These instructions I1, I2, I3. Okay, I3 is our branch instruction. Okay. So what we are going to do, so let me make a pipeline diagram again. So what I am saying, I1, I2, I3, and I3 is our branch, and it is branch target is I10. Is I10. Okay, so let me make a pipeline diagram here. This is instruction fetch, operand fetch, execute, memory access, and write back. So these are our cycles 1, 2, 3, 4, 5, 6. Let me make some more cycles. 7. Okay. So let's see, in cycle 1, I1 will be fetched. In cycle 2, I2 will be fetched. In cycle 3, I1 will be in execute. I2 will be, I3 will be fetched. In cycle 4, I1 will be fetched. I1 will move to, in cycle 4, I1 will move to memory access stage. I2 will move to execute. I3 will move to operand fetch. Now, when we are fetching this I3, okay, so after fetching an I3, we will find out that this I3 is a branch instruction. It is a branch instruction. Okay, so whenever a branch instruction is taken, whenever a branch instruction is fetched, okay, we will stop the fetch stage. Okay, so our instruction I3 is, what is this instruction? It is a branch instruction. So we will freeze the instruction fetch stage. Okay, so in 4th cycle, it won't fetch anything. Now, in the 5th cycle, I1 will come here, I2 will come here, I3 will come here. Okay, again, we will keep this fetch stage in freezing mode. Okay, now I3, this instruction was our branch instruction. This instruction has reached into the execute stage. So when this instruction is in execute stage, in the execute stage, we will be knowing whether the branch is taken, or not. So in the execute stage, for example, if we know that the branch is not taken, then what should be the next instruction? Next instruction should be I4. However, if the branch is taken, then next instruction should be branch target. And what is the branch target? I10. So in this execute stage, we will be knowing what should be the next instruction. Should it be I4 or should it be I10? Now let's say we know that the branch is taken. So what should be the next instruction? Next instruction should be I10. So we are sure that the next instruction is I10. So after this execute stage of I3, so what is the next cycle? Next cycle is 6th cycle. So in 6th cycle, we will know what is the actual instruction that is to be fetched. Okay, so in the 6th cycle, my I2 will come to write back and I3 will complete its execute and will come to memory access. And in the same stage, we will be sure what should be the next instruction. Let's say the next instruction is I10, or we can say the branch is taken. Then the instruction that should be fetched should be I10. So you can see that because of this branch, how many cycles we have lost? We have lost 2 cycles. Okay, so we have to stall the pipeline for 2 cycles to handle control hazard. Okay, and then our pipeline will move as it is. So because of branch, so we will have two extra cycles, or we can say we have to stall the pipeline for two cycles. Why two cycles? Because in two cycles our branch instruction will come into the execute stage, and in the execute stage, after executing that particular branch, we will be sure what is the next instruction, whether the branch is taken or not. So every branch results in two extra cycles. Okay, and this is a scenario when we are handling the control hazard by stalling the pipeline. So this is one solution. One solution to handle the control hazard is to stall the pipeline. However, this solution results in two cycle penalty for every branch instruction. Fine. So this is one solution. Now let's see the second solution. The second solution is called a delayed branch. Okay, so before explaining delayed branch, so let's go back here. So you can see that in these two cycles, cycle 4 and 5, okay, our pipeline is idle, or we can say we have lost two stages, so two cycles. Okay, so these two slots are called delay slots. So these two extra cycles in which our pipeline is empty are called delay slots. Okay, so because of a branch instruction, there are two delay slots. Okay, or in other words, we can say that whenever we have a branch, let's say branch, this instruction is fetched, then for next two cycles, we don't have to fetch anything. So there is, these two cycles are called, or these two pipeline bubbles are called delay slots. Okay, so why we don't have to fetch anything? Because we don't know what will be the next instruction executed after the branch. Okay, now let's see what is delayed branch doing. So it is saying, let's say we have instruction I1, okay, instruction I2, instruction I3, instruction I4 is branch. Then we have I5, then we have I6, then we have I7. Let's say the target of this branch is I7, I7, I8, I9, and so on. Okay. Now let's see what is that stalling the pipeline solution doing. So we are fetching I1, then after I1 we will fetch I2, then we will fetch I3, then we will fetch I4. Okay, so when we are fetching I4, what will be the next instruction that we will fetch? We won't fetch anything in for next two cycles. So in next two cycles we won't fetch anything. Why we are not fetching anything? Because we want this branch to go into the execute stage. Then only we will be knowing whether we have to execute I5 or we have to execute from I7. Now let's say this branch is taken. If the branch is taken, okay, this I4 branch is taken. Then what instructions we have to execute? So after I4, what is the instruction that we have to execute? We have to execute I7, I8, I9, and so on. However, if the branch is not taken, then what are the instructions that we have to execute? We have to execute I4, I5, I6, I7, I8, I9, and so on. Okay. So you can see here that from these two scenarios, either we have to execute this or we have to execute this. And in these two, you can see that these instructions, I7, I8, I90, I9, they are executed whether the branch is taken or branch is not taken. So these three instructions, I7, I8, I9. So I7, I8, and I9, and many more, let's say many more instructions. These are the instructions that are executed irrespective of the branch. Irrespective of the branch. Or we can say irrespective of whether the branch is taken or not taken. So these instructions are taken irrespective of the nature of branch, whether the branch is taken or not taken. So let's do one thing. So these two delay slots where we are not fetching anything, let's put those instructions here, those instructions which are executed irrespective of the output of this branch. But those two instructions should be independent instructions. They should not result in some other dependency. Okay, so we have to take some instructions from this set which is common between the taken and not taken path. Okay, so we will take those instructions. Let's say we will keep I8 and I9 here. Then let's see what will be the final output. Let's say we have fetched I1, then we have fetched I2, then we have fetched I3, then we are fetching I4. Okay, so after I4 we were waiting for 2 cycles. However, in this scenario, what we are saying, we won't wait for 2 cycles. We will fetch I8, then I9. Okay, so let me make a pipeline diagram. Okay, in the first cycle I am fetching I1, in the second cycle I am fetching I2, in the third cycle I am fetching I3, in the fourth cycle. So in the fourth cycle, in previous scenario was stalling the pipeline. So sorry, our instruction is I4 is our branch. So in the fifth cycle, I1 will come here, I2 will come here, I3 will come here, I4 will come here. In the previous scenario, we were saying when we were stalling the pipeline, we were saying whenever a branch is there, we won't fetch anything for 2 cycles. Okay, so the scenario would have been that in the 6th cycle, I1 will complete, I2 will come here, I3 will come here, I4 will come here. So in these 2 cycles, we were not fetching anything. However, here I am saying I will bring 2 instructions such that those 2 instructions are executed always, irrespective whether the branch is taken or not taken. So let's say those 2 instructions are I8 and I9. So when I4 is executed, I will fetch I8. Because I8 will always be executed whether the branch is taken or not taken. Then in the 6th cycle, I will fetch I9. Now in the 7th cycle, this will complete. Okay, I3 will come here. Now at the end of 6th cycle, I4 would have found out what is its actual instruction that is to be executed. If the branch is taken, what should be the next instruction? If the branch is taken, the next instruction should be I7. So next instruction that it is going to fetch will be I7. This I9 will come here, I8 will come here, I4 will come here. Okay. So after I7, this I8 and I9 are to be executed. So since these has been already moved to this location, so these two won't be executed. They will already be there in the pipeline. Okay. So now let's say if the branch is taken, if the branch is not taken, then what should have been the instruction that is to be fetched? The instruction that is to be fetched is I5. Then after I5, what should be the instruction? I6. Then I7, I8, I9. Okay. And these I8 and I9 are already in the pipeline. So these two instructions are already executed. So, or we can say they are always executed irrespective of the branch outcome, whether the branch is taken or not taken. Okay. So what we have done, whenever we have a branch, since we were after this branch, we in the usual case, the next instruction that is to be executed would be the outcome, would be based on the outcome of this branch. If this branch would have been taken, the next instruction should have been I7. However, if the branch is not taken, the next instruction should have been I5. However, what we are doing, we are saying that after this branch, the next instruction that should have been the actual instruction to be executed, we are delaying it. We are saying that let's execute some other instructions. Those two instructions should be independent of the outcome of this branch. So we are delaying the execution of the outcome of this branch. Or we can say we are delaying the instruction that should be executed. We are executing that particular instruction after these two branches. So that is why this solution is called a delayed branch. Why it is called a delayed branch? Because the next instruction that should be executed after the branch should have been the instruction depending upon the outcome of this branch. But that instruction, for executing that instruction, before that instruction, we are executing some other instruction. So we are delaying this particular instruction. So this is called a delayed branch. And you can see in the pipeline, because of this delayed branch, are we losing any cycle? No, we are not losing any cycle. So this particular solution not only handles the control hazard, but also it does not result in any penalty. Okay, the previous solution where we were delaying the where we were stalling the pipeline, that particular solution was also able to handle the control hazard, but that was resulting in 2 cycle penalty. And this delayed branch, this handles the control hazard, and it also does not result in any penalty. But the only thing that we have to do, our compiler has to do, is that it has to find these 2 instructions, the instructions that are independent of the outcome of this branch. Okay, that is the only job that the compiler has to do. But the limitation is that for compiler, it is not always possible to find these 2 instructions. So our compiler won't be able to handle the control hazard using the delayed branch technique always. Okay, so we cannot handle this particular control hazard using a delayed branch all the time, because sometimes it may find 2 instructions to fill 2 delay slots, but it is not always possible for a compiler to find these 2 instructions. Okay, so whenever our compiler is not able to fill these two delay slots, we have to move to the previous solution. And what was the previous solution? The previous solution was to stall the pipeline. Okay, so these were the two solutions that we are trying to handle the control hazard. There is another solution that is trying to handle the control hazards, and that particular solution is the branch prediction. So let me first repeat what we have discussed so far, then we will discuss about the branch prediction. We discussed two solutions, and solution one was to stall the pipeline. Okay, this was solution one, and second solution was delayed branching. So these were the two solutions that we discussed in our previous lecture. Okay, one was related to stalling the pipeline and another was related to delayed branching. And in these two solutions, for example, let's take the example of stalling the pipeline. In this particular scenario, we were able to handle our control hazard, but it resulted in a penalty. And that penalty was for 2 cycles. So we have 2 cycle penalty when we are stalling the pipeline. However, in delayed branching, what we were doing, we were inserting 2 instructions after the branch. Okay, so after the branch, we were inserting 2 instructions, and those instructions are the feature or the characteristic of those 2 instructions is that those instructions are always executed irrespective whether the branch is taken or not taken. And these 2 instructions are found out by the compiler. However, we said that the negative side of this delayed branching is that our compiler won't be able to find 2 independent instructions all the time. So in that scenario, we have to stall the pipeline. The third solution that we are going to discuss is the branch prediction. Okay, so this particular solution we have to discuss. And for discussing this solution, let's take this as an example. Okay, so this is the example. So we have instruction I1. Let's say we have a program, we have instruction I1, then I2, and I3 is our branch. Let's say the target of this branch is I10. Okay, this is the target of this branch. Now let's see what we are doing. So let me make a pipeline. So this is our pipeline. So these are the 5 stages of the pipeline. So I'm making the 5 stages here. So this is instruction fetch. This one is operand fetch. Then we have execute. After execute, we have memory access, and the last stage is write back. This is write back. So these are our 5 stages. Fine. And let me make the arrow from one stage to another stage. Okay, so our main aim is to handle a branch instruction. So let's say a branch instruction comes to instruction fetch. Okay, so after instruction fetch, what we are doing in this particular scenario, stalling the pipeline. So when a branch instruction comes, we will allow this branch instruction to reach to execute stage. Okay, so when a branch instruction is fetched, let's suppose it is fetched in cycle 1. Okay, then in cycle 2, this branch instruction will reach to operand fetch, and in cycle 3, the same instruction will reach to branch, to the execute stage. Okay. However, whenever a branch is coming, what we are doing, we are stalling the fetch stage. Okay. So we are stalling this fetch. We are not allowing this fetch to get any instruction till this branch reaches the execute stage. In the execute stage, branch knows whether, or we can say we know whether the instruction is taken or not taken. So in the execute stage, we will know the outcome of the branch. What is the outcome of the branch? Okay, so based on this outcome, we will decide what should be the next instruction that is to be fetched. So when branch instruction completes the execute stage, then in the next cycle, this branch moves to memory access and we will fetch a new instruction. Okay, this new instruction will be a branch target if the branch is taken. However, it will be a next instruction if the branch is not taken. Okay, so we have to keep these two cycles, or we can say that whenever a branch is fetched, then for the next two cycles we are freezing the instruction fetch stage. We are not allowing the instruction fetch stage to fetch the next instruction. And why we are not allowing it? Because we don't know what should be the next instruction, whether the next instruction is I2 or it is I4. Okay, so we don't know, and we know we are confirmed only at the execute stage. So at the execute stage, we will know whether the instruction that is to be executed is I10 or whether it is I4. So that means in the execute stage, we will know whether the branch is taken or not taken. Okay, and if the branch is taken, then what should be the next instruction? The next instruction that should be fetched should be I10. However, if the branch is not taken, then the next instruction that is to be fetched should be I4. So what is the issue of branch instruction? So the issue of branch instruction is that when this branch instruction is in fetch stage, okay, when this instruction is in fetch stage, in the fetch stage itself, so when this instruction is in fetch stage, we don't know, whenever branch instruction is in fetch stage, we don't know what should be the next instruction. Okay. However, in the fetch stage, if we know what will be the next instruction, we won't have any extra delays. Okay, so what I am saying, for example, if an instruction I1 is fetched, when I1 is fetched, so for example, I1 is here, then when this I1 moves to operand fetch, we are sure what will be the next instruction, and next instruction is I2. So our fetch stage can easily fetch this I2. Okay, however, when there is a branch instruction, okay, and when this branch instruction moves from instruction fetch to operand fetch, after that we don't know what will be the next instruction, whether the next instruction is directly the next to the branch or it is this branch target instruction. So if in the fetch stage itself we are able to get the outcome of a branch, okay, if we are able to know the outcome of the branch, then we will be able to answer whether the next instruction is I10 or the instruction is I4. So what I am saying that if in the instruction fetch itself for a branch instruction, if we are able to know this scenario, whether the branch is taken or not taken, then we will be able to fetch the next instruction quickly after the branch instruction, or we can say we don't have to include any delay, or we say we don't have to stall the pipeline. But the issue is that the outcome of the branch is not known in the fetch stage. it is known only in the execute stage. Okay, so let me repeat the same. I am saying that if I have a branch, okay, and if I know the outcome of the branch, for example, if I know the branch is taken, then what should be the next instruction? The next instruction should be item. And if I know the branch is not taken, then what should be the next instruction? The next instruction should be I4. Let's say this instruction has been fetched. So this branch instruction has been fetched. Okay, so this particular branch instruction. So let's say it is instruction I3. So this instruction has been fetched. So when this instruction is fetched, after completing the fetch, this instruction will move to I3, this operand fetch. This I3 will move to operand fetch. Now, for example, if I know in the fetch stage whether this branch, this I3 is taken or not taken. Let's say in the fetch stage, I know the branch is taken. Then what should be the next instruction? The next instruction should be I10. So since in the fetch stage itself, I know that the next instruction after I3 is I10. So when I3 goes to operand fetch, I will also operand fetch, I will fetch the I10. Okay, so you can see then I3 moves to execute and I10 moves to operand fetch. So is there any delay or is there any bubble in the pipeline? No, there won't be any bubble. Why? Because my instruction fetch stage is not idle. But this scenario, this particular scenario is possible only if I know the outcome of branch in fetch stage. So if I know the outcome of this branch in fetch stage, then in the fetch stage itself, I will know whether the next instruction is I10 or I4. However, we don't know the outcome of branch in a fetch stage. We know the outcome of a branch in execute stage only. So the outcome is known in the execute stage, not in the fetch stage. So what will we do? Let's see what will we do. We will do a prediction. Okay. What prediction? A branch prediction. So how will we achieve this? For example, let's do this. Let's say whenever a branch is coming, or we can say whenever a branch is fetched. So in the fetch stage, we will make a prediction for this branch. Okay. So what will be the prediction? Prediction will be whether the branch is taken or not taken. Okay. So we are making a prediction. And in which stage we are making a prediction? In the instruction fetch stage. Let's say branch has come here. And I am making a prediction that whenever a branch comes, let's say one prediction, I will give one example. I will predict the branch is taken. Okay. So in the fetch stage, I am predicting the branch is taken. It is taken. Okay. So when a branch is taken, what will be the next instruction that is to be fetched? We have to fetch I10. So I am predicting the branch is taken, and because the branch is taken, what will be the next instruction? The next instruction is I10. Okay. So this is my prediction for branch in the instruction fetch stage. Now, when this branch reaches into the execute stage, in the execute stage, we will have actual value of the branch. Actual means we will have the confirmed value whether the branch is taken or not taken. So what was my prediction? My prediction was branch is taken. And in which stage I have made this prediction? I have made this prediction in fetch stage. And because of my prediction, I was able to fetch the next instruction without any pipeline bubble, or we can say without any delay. However, in the execute stage, we will know the actual outcome of the branch. Now, if the actual outcome if this actual outcome is equal to my prediction. Okay, if actual outcome is equal to my prediction, then that means I have correctly predicted. So I have correctly predicted. What I have predicted? I have predicted the outcome of a branch. Okay, so my prediction is correct, and because of my good prediction, I won't be having any issue in the pipeline. However, if my prediction is wrong, let's say actual outcome is not equal to predicted outcome. So what was my predicted outcome? My predicted outcome was branch is taken. However, I am saying actual is not equal to predicted. So actual would have been branch is not taken. Now, because of my prediction, I have fetched I10. However, actually this branch is not taken. So what should be the next instruction? The next instruction should have been I4. However, I have fetched which instruction? I have fetched I10, and let's say after I10, I have fetched I11. Okay, so these two instructions. So now, for example, I10 has reached to operand fetch, and I11 is in instruction fetch. Okay, let me repeat this to make it clear. So I will make a pipeline diagram also here to help you understand it easily. Okay. Let's make a pipeline diagram here. To make you understand it clearly. So this is my cycle 1, then cycle 2, cycle 3, cycle 4, cycle 5, cycle 6, cycle 7. So let's start from this instruction. So the branch instruction. Okay, I3 is branch. And let's say I3's target is I10 and I11. Now let's see what we are doing. So when an instruction is fetched, let's say I3 is fetched. Let's leave these two instructions, I1 and I2. So I3 has been fetched, okay, in the first cycle. So in the fetch stage itself, I am making a prediction for this instruction. Prediction whether the branch is taken or not taken. Let's say I have predicted the branch is taken. Okay. So that means if I predicted that the branch is taken, so what should be the next instruction according to my prediction? The next instruction should be I10. So in the next cycle, I3 reached to operand fetch, and I have fetched I10 because I predicted the branch is taken. So the next instruction that is to be fetched is I10. Now in the third cycle, I3 reaches to execute stage, I10 reaches to operand fetch, and after I10 which instruction is to be fetched? I11. Okay, so till now, till this third cycle, my instruction has reached to execute my branch instruction, the instruction for which I predicted that the branch is taken. So because of my prediction, I have fetched I10 and I11. Okay, it is my prediction. Now at the end of this execute stage, okay, when my branch instruction is in execute stage, in this stage I will know the actual outcome of the branch. Okay, so in execute stage I will have actual outcome of the branch. So let's denote the actual outcome by A. Now if we see, if my actual outcome is equal to my prediction, if my actual outcome is equal to prediction, so what was my prediction? My prediction was branch is taken, so that means actual outcome is also branch is taken. So if the actual outcome is also branch is taken, then what should be the next instruction after I3? So the next instruction should have been I10 and I11. And if you can see in the diagram also, we have the next instruction is I10 and I11. Fine. Okay, so if our prediction is true, if my prediction is true, then we have saved two cycles, two penalties, because in the previous case, whenever we have a branch instruction, we have to wait for two cycles. Our fetch stage has been freezed for two cycles in the previous scenario, but here we are not freezing the fetch stage. We are allowing this fetch stage to fetch the instructions based on our prediction. And if our prediction is true, that means we have saved how many cycles? Two cycles. Okay, now let's see if actual outcome is not equal to predicted outcome, or we can say my prediction is false. Okay, what will be the issue? If my prediction is false, what was my prediction? My prediction was the branch is taken. However, the actual prediction will be branches not taken, because I am saying actual is not equal to predicted. I predicted the branch is taken, so the actual outcome was branch is not taken. So actual the branch is not taken. So what should be the next instruction in actual for the correct execution? The next instruction should have been I4. However, what is the next instruction in our pipeline? The next instruction is I10. Okay, so that means when this instruction has ended in the execute stage, which instruction? Branch instruction. If my prediction is false, that means whatever I have fetched because of my prediction, that fetch or those instructions are on the incorrect path, because I have predicted the path should be this one. However, the path is this one, sequential one, because I have predicted wrong. So that means whatever is in the instruction fetch stage and operand fetch stage, I have to remove those instructions. Okay, so we can say we have to flush the pipeline. Flush means remove everything from the pipeline. Because why we have to flush the pipeline? Because our prediction is wrong, and because of my prediction I have fetched those instructions which should not have been executed. So that means I have to remove those instructions from the pipeline. I will allow this instruction to go forward in the pipeline, but I will remove no, sorry, I won't allow this instruction to go forward in the pipeline, but instead I will remove all the entries from the pipeline. So I will remove I3, I10, I11 and everything whatever is in the pipeline, and I will again start from I3. Okay, so in the fourth cycle I will start from I3. I will fetch I3, and now I will predict. My previous prediction was I3 is taken, and but that prediction was wrong, so the next prediction is I3 will be not taken. So then it will easily go into the pipeline. So we can see that if my prediction is correct, if our prediction is correct, then we have saved how many cycles? 2 cycles. Okay. However, if my prediction is incorrect, so that means in that scenario, we have to flush the pipeline. And because of flushing the pipeline, we have penalty of cycles. Let's say we have X penalty. X number of cycles have been lost because of flushing. Flush means remove everything from the pipeline, remove all the instructions from the pipeline. Okay. Fine. So you can see that using a prediction, branch prediction, I can save 2 cycles for each instruction. However, the scenario is that my prediction accuracy should be very high. Very high. Okay, my prediction accuracy should be very high. Then only I can save the cycles in my while having a branch instructions, and as a result, there will be an improvement in the IPC, or we can say there will be an improvement in the performance of the system. Okay, so let me summarize this. Let me summarize my branch prediction. So what is branch prediction doing? So wait a second, I will rub this. So branch prediction. What does it mean? It means predicting the outcome of the branch in which stage? In fetch stage. Okay. However, the scenario is that if my branch prediction is correct, if I have correctly predicted the branch, then I will save how many cycles? 2 cycles. However, if the prediction is incorrect, then that means I will be resulting in flushing the pipeline. I have to flush the pipeline. Fine. And as I said, this branch prediction, the program, or we can say the hardware that does the branch prediction, is called branch predictor. And this hardware is there in the fetch stage. So our fetch stage has 2 functionalities. It is fetching the instructions, it is doing the instruction fetch, and it also has a circuit doing a branch prediction. Okay. So when an instruction is fetched, my fetch component will fetch the instruction and my branch component will predict the outcome of the branch. And based on its prediction, it will update the program counter. Okay. For example, if the branch is not taken, if it has predicted that the branch is not taken, then the next instruction should be the next instruction that is next to the current instruction. However, if the branch is taken, if I have predicted that the branch is taken, that means the next instruction should be at the address denoted by the branch target. Fine. So in computer architecture, there are many branch predictors. Okay, there are different types of branch predictors in computer architecture. So let me write some of the branch predictors here. So we don't have to discuss the branch predictors in in this course because that is out of scope of this course. So let's say one type of prediction, one type of branch predictor is such that which is saying that let's predict the all branches as not taken. So whenever a branch comes, we will predict the branches not taken. Okay, that is one prediction. The second type of predictor is which is saying let's say let us predict that all branches are taken. This is another kind of predictor. Okay, the third kind of predictor is, so these are the trivial predictors. However, there are well sophisticated predictors. I will name those predictors, but it is your job to search the internet and find out about those predictors. Okay. So the third branch predictor is such that it is saying that if a branch is forward branch, okay, if a branch is forward branch, then take this branch as not taken. Okay. However, if the branch is backward means going back in the program. If the branch is backward branch, then predict this branch as taken branch. Okay. So this is a third predictor. The fourth predictor, these predictors are static predictors. Static means we don't have to look at the program. So they don't depend upon the nature of the program. Okay. So whatever the program is, whenever branch comes, we will predict a not taken in this scenario. And in this scenario, in this prediction, we will predict the branches taken and likewise in third. However, there are dynamic predictors as well. Dynamic means that they predict the branch during the runtime based on the nature of the branch. Okay, so there are different predictors. For example, there are 1-bit predictors, there are 2-bit predictors, okay, and the third is saturating counter based predictor, saturated counter. The fourth is global predictor. The fifth is, there are different versions of global. For example, Tage is another predictor. There is another predictor called tournament predictor. And the seventh is hierarchical. There are many other predictors in architectural community. However, in this particular lecture and in the undergrad course, these predictors are not, are we can say out of scope for the undergrad course. But yes, if you are interested, you can go on the internet and look at these predictors. But one thing I will be presenting here, that how these predictors are going to work. So for every prediction, let's say in machine learning or in any system where we have to predict, the first thing that we have to do is to train our predictor. So let's say I have a predictor. Okay. The first thing that I have to do is to train this predictor. And for training any predictor, we have to use the data. Okay. In the architectural community, what we do, we have some standard programs. Okay. Standard programs. Those programs are called benchmarks. Okay. And we train this predictor using these standard programs, or we can say using the benchmarks. For example, one benchmark is spec. Spec is one benchmark. Another benchmark is parsec. Okay, another is splash, and there are many other benchmarks. Okay, so first we train this predictor on these benchmarks. After training, we make this predictor to predict during the runtime. So whenever our program is running, we will predict based on our predictor. The predictor that has been trained using these benchmarks, standard programs in architectural community. Okay, so this completes our discussion about the branch prediction. However, as I said, that if somebody is interested, he can surf the internet and see the meaning of these branch predictors. Take one or two from here and learn about these one or two predictors in great detail, and that will help you to understand the working of these branch predictors. Okay, so this completes our part B of lecture number 20, in which we were discussing about the branch prediction. Okay, branch prediction means predicting the outcome of the branch in fetch stage in order to handle the raw hazard, sorry, in order to handle the control hazard, and also help us to save 2 cycles. Fine. And as I said, if my branch prediction is incorrect, then I have to flush the pipeline, and there will be associated penalty with flushing the pipeline, because flushing the pipeline is an expensive operation. We will lose many cycles while flushing the pipeline. So our branch prediction accuracy should be very high. Then only we will be able to achieve a good improvement in the performance. So with this lecture, we completed our branch prediction and a mechanism to handle control hazards, and also we completed our discussion about the processor pipelining. In the next video or in the next lecture, we will be starting we will start the discussion about the memory systems in our computers. Okay, so let's meet in the next lecture. Till then, goodbye.